Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone. We're going to go on talking about continuous random variables and try to get through quite a lot of ones that come up all the time. And the one that comes up most often is the normal distribution. So, by the way, that proof last time, which got a little bit truncated at the end, is not examinable. In fact, I said I won't ask you to repeat any of the proofs from class in any test, but that's to see where this kind of even minus half x squared comes from. So the normal distribution, there are many different normal distributions, but they're all related. In fact, on the real line, they're all related by very simple operations, stretching and scaling. So, and then there's also the standard, as the notation suggests, x is a general normal distribution has a mean parameter, expected value of x is mu, and the variance of x is sigma squared. So we put the variance as the second parameter. That's a convention. So like you'll find on R they use the standard deviation rather than the variance. It's just a matter of square root. And then there's the standard normal distribution. And that's the same thing with mean 0 and variance 1. And we often use the letter z for it. People even say z is for just as a shorthand way of saying it's a standard normal or something that is approximately standard normal. Now, the density function of z is so common that we often use the little lowercase phi, although it's not strictly reserved for this. The little lowercase phi of z is equal to 1 over square root 2 pi, which is a normalizing constant. You can get it like in the derivation you can get it from Stirling's formula, but in fact, it's just a matter of fact that's the only constant which makes this integrate to 1. The key part of it is e to the minus a half z squared. That is the formula. So, density of the standard normal. If you want the density of a non-standard normal, we'll have to stretch and scale. I'll show you how to do that in a moment. But I think this is the only one that's really worth remembering, because the other one is just a manipulation of it. Okay, so the concept, because we know that the integral minus infinity to infinity of 5 z dz must be 1, that's a property of density functions. It's so this constant is determined that there was no other choice for it. Interestingly, if you actually try to integrate that function, you'll find it difficult. And let's talk even about the cumulative distribution function of the standard normal. That cumulative distribution function is called capital phi by convention. I could call it also f capital Z, capital phi, Z, just because it's common. It's related to something called the error function in analysis, and it doesn't have a closed form. That's nothing bad. It just means you can't express it in terms of sums, products, multiples, divisions, powers, those kind of basic things. You can't even, not even in terms of exponential and trigonometric functions, it's just its own new function. So by definition, this is of course the probability that a standard normal is less than or equal to z. So it's minus infinity to z of 5z, which I can write explicitly, squared over root 2 pi d. I better make this t rather than z. Just a dummy variable t. So, which is of course the same as the probability that capital Z is less than or equal to z. Now, as I say, there's no known, well, not no known. It can be proved that there's no primitive of this. There's no antiderivative of that in terms of elementary functions that we know. On the other hand, every continuous function has an antiderivative just as a function. So this certainly exists. We just don't have it's a function, so every input it gives you an output. We just don't have any very good expression for it other than capital phi, and that's kind of why that's the greatest. Okay. So this, of course, the thing I'm trying to sketch is 1 over root 2 pi e to the minus x squared over 2. Okay, so that's x and y. It is, of course, symmetric about the origin, nothing surprising about that. And if you wanted, so the height here is, which is little phi. So I've graphed little phi, but the cumulative distribution function is the area under the curve. So this is z, and that area is capital phi. So the graph of capital phi itself, there's a relation between, so that if you do y and x, and then I have capital phi. Obviously, capital phi is always between 0 and 1. The shape of this curve has a special name. So now if I'm trying to sketch y equals capital phi of x as a graph, then the corresponding thing, because of the symmetry, capital phi of 0 is 1/2. Because any curve that is symmetric around the origin, we know that the total area is 1, therefore it must be half the area to the left, half the area to the right. Now, this is the shape of the cumulative standard normal distribution function, and I think this is not exactly to scale, perhaps I okay. So just imagine that it's like that. I won't be specific about what the x scale is, and then it's still conceivably true. This shape is called a sigmoid curve. Okay, that's a description of the shape. There are other sigmoid curves. This is not the only one. The other examples, something like hyperbolic tangent, that's actually a sigmoid. It goes from -1 to 1. It has the same kind of shape. Sigmoid means looks like an S. You might not think that looks much like an S, but anything with a positive curvature first and then a negative, like a positive second derivative to start with, then going down to a negative second derivative, makes sense that you call it somewhat S-shaped. Okay, So we use that all the time, and there are tables. Calculate phi of z. For the purpose of this course, it's you have tables of phi of all these. Essentially, you can do it for 2 digits. By the time you get to phi of 3, that's the probability of being less than or equal to 3. That's about 99.85%. So there's not much point tabulating it beyond 4 or so and beyond -4. But you will get these tables on the exam. I didn't bring it with me here, but you would have all used them in your first statistics course. Now, that's all well and good for finding probabilities given a x coordinate or a z. You can go the other way, and that's called the quantiles. So I might refresh your memory about quantiles. Okay, so you forgot. Quantiles of a distribution. If Q is between 0 and 1, then a Q quantile, I'll just call it X, but of a random variable X, or it could be it just depends on the distribution. You can also say the quantile of its distribution is a value X such that, now I guess the exact definition would usually be the following. There are slight variants, especially if you're doing a sample quantile, which is a bit different. But a theoretical quantile is just this: the probability that X is less than or equal to X as the okay, if at all possible, you can do this. Now, for a continuous random variable, because it's a continuous random variable, there's no chance that you actually land on a particular point. So you can always just, capital F is an increasing function. You can always just find the single x value at which it jumps past that point. The only wrinkle with this is you have to be slightly more general for a discrete distribution. The reason is, if you just think of something like a forget about continuous and discrete. I'll just say, slightly more generally, you might sometimes need probability of being less than or equal to x should be at least q, and also the chance of being greater than or equal to x should be at least 1 minus q. That will resolve any wrinkles if it's not possible to solve it exactly. You can always solve this even if you can't necessarily solve that exactly. But let's just don't worry about the more general case. We'll just follow on star. If star holds, this will certainly be the case if you've got an increasing continuous function, capital F, that doesn't just sit at any fixed value, holds, then the qth quantile of this x, or of a distribution, is nothing other than the inverse cumulative distribution function evaluated at q. Remember, fx inverse says find an input such that the cumulative distribution function at x equals q. So that's finding an x value, so the chance of being to the left of x is q. Now q, of course, the 1/2 quantile has another name. This is called the median. Okay? The median is shorthand for 50% of the chance less than it and 50% greater than it. And then you have also a first quartile, which is, and people will talk about percentiles too. So first quartile is 1/4 quantile. So these are all special cases. Third quartile. I have to write out the whole word because quartile and quantile are very. I still haven't fixed that. quantile and quartile are very similar words. And of course there's the p percentile, for instance, which you would be familiar with from university entrance or anything, p over 100 quantile. So for continuous distributions that could land on any real number, there's no problem at all defining this. And that's what we use quite a lot in hypothesis testing, which we'll talk about at the end of the course. You're probably familiar from the first one, but we want to find a value so that the chance of being, for a standard normal, for instance, the value such that the chance of being larger than that value is only 5%. That value is about 1.68, or maybe it was 1.64. And then you can also do a symmetric one, the region outside which the chance is of being, you want 95% confidence intervals, so that means 2.5% to the right, 2.5% to the left, and your interval in standard coordinates goes from -1.96 to 1.96. So those are examples of quantiles. So e.g., the 97.5th percentile of normal 0, 1 is phi inverse of 0.975, approximately 1.96. That would be good enough precision for anything you needed to do. And you can find that in the table. You look at 1.96 in the table and you'll find phi, but it's pretty close to that. Okay, so that's the basics of the normal, which are probably quite familiar to you. Let's do a few interesting things about finding related random variables. The first thing is I haven't given you the one that that gives you the non-standard normal. Maybe before I talk about shifting and scaling, we'll do a little bit of an exercise. So we can do an exercise in, I'm going to do the mean and variance of the standard norm because I've just asserted that they're 0 and 1 respectively. Let's do it by means of moment-generating functions, which once again, that's not a discrete versus continuous thing. It's just whenever the moment-generating function exists around the origin, you can use it to calculate it. So exercise in MGS. Now, there's a slight trick involved in doing the MGF of the standard normal. Let's do it. If we have Z is normal 0, 1, a reminder that phi, the density is either minus a half Z squared by square root 2 pi. And you just remember that this thing integrates to 1. It's easy to forget. So that's useful in evaluating the MGF. M subscript Z of little z. So, MGF takes conventionally T as a parameter, is expected value of the exponential e to the T times the random variable. Remember that? It's a function of T, but it depends on the exponential of the random variable expected value. So I just need to write an integral for what that is. The possible values of Z are all real numbers. And when we say possible, I mean even remotely possible. That's everywhere where the density is positive. As a matter of fact, because e to the minus Z squared is so quickly decaying that it's vanishingly unlikely to be more than a few standard deviations away. That's quite unlike some other random variables. But here, there's just very little chance of being in the tail. But it is positive, and so because it's positive, I still need to include that in the integral. So minus infinity to infinity. Then I'll put the density here, e to the minus a half Z squared divided by square root 2 pi dz. And what do I have to multiply by the density again? Any takers? An expected value is always, to do an expected value, you always have to take value times probability, and you either add that up or integrate it out. So, exactly, e to the t little z. So it's easy as pie to take the expected value of a function. You just do integral function times density. Function of z is equal to tz, density is either minus half z squared over 2 pi. What you do next is not quite so obvious, but if you've done a lot of calculus exercises, you'll be very familiar with the fact that if you don't know what to do with something that involves quadratics, what's the most useful operation you can do to a quadratic? I'll put the 1 over root 2 pi at the front because that's a constant. most useful operation on quadratics. How do you solve a quadratic equation? Just not calculus, just, you know, ax squared plus bx plus c equals 0 or constant. How do you solve it? Someone's probably going to say the quadratic formula. Is that right? How do you derive the quadratic formula? There's a name for it. I mean, maybe you don't know the name, but solving a quadratic is particularly easy when it's of the form x squared equals constant. Right? It's harder when it's x squared plus something times x equals constant. So how do you make the hard case into the easy case? Okay, well, the name is completing the square, probably. Anyone have the name completing the square? Yeah, 2 nods. Okay, completing the square means you don't want the z squared and the z, you just want a single thing squared. That's a lot easier to deal with. Because it's just, you know, whether it's z or z minus something is just as easy to deal with. So let's complete the square. Yeah. Okay. When you complete the square, I'm not going to be able to do anything about the half. In fact, there's a minus 1/2 as the coefficient. And then I need to put in something. The main term that I need to take care of is the linear term. That's hard. Because z squared, and then what do I subtract? T is correct, because then I will have z squared minus 2zt. Luckily, there's a 1/2 to take care of the 2zt. And I have polluted my equation with a constant term that was, you know, there's an extra term present here, minus 1/2 t squared, which wasn't there, present there. So I better add on plus 1/2 t squared to solve that issue. So that's completing the square is a classic thing that you do to solve an integral. So I can even put that out in front. E to the 1/2 t squared divided by the square root of 2 pi. Integral minus infinity to infinity minus 1/2 z minus t squared. And the first thing to do, whenever you have a shifted, there's two things that I'm going to do. I'm going to bring the root 2 pi back inside the equation. And it's common, remember t is a constant. As far as, you might think, of course t is not constant, it's the input to the equation. But while you're doing the integral, it's still constant. It's only later that you differentiate. You first do the integral with a constant t to evaluate mz of t. T can come out, but z is not constant. Z minus t has the same, you know, a shifted integration variable is the same as a non-shifted integration variable. You could, if you like, you can do the change of variables u equals z minus t. But, you know, the shift doesn't change anything. E is minus 1/2 u squared over root 2 pi du. Does this ring a bell? Is it clear why I brought the 1 over root 2 pi back inside the equation? If anyone thinks it does ring a bell, can you tell me what this is? It's just 1, yeah, and that's because I am integrating a density function. Yeah, specifically the density. I'm integrating little phi. This is equal to 1 because all density functions integrate to 1. That's a part of the definition of a density function. Okay? So this is nothing other than minus infinity to infinity phi of u du. Phi is the fancy name because this is the normal density function, but every density function integrates to 1. So this trick works particularly well with normals, but you can use it whenever. If you just have either a sum of a PMF or an integral of a PDF, you can say straight away that it's 1. You don't have to justify that anymore. Of course, you might wonder, in terms of not being able to actually do the integral, how that is 1. So we're using previous knowledge here from the fact that it is a density function. To actually justify that integral by other means, there's various tricks. You can do a 2D polar coordinate thing. So you can worry about that in your calculus class. I won't worry about it here. So nevertheless, so that factor was equal to 1. That factor was equal to 1. So the moment generating function is e to the 1/2 t squared. Now, there was no assumption on t necessary here. Remember, sometimes the MGF fails to exist, but here, regardless of what t is, we can do that. Change of variables and find the integral. Okay, so that's mz of t. Let's use this to find the mean and variance at the very least. Well, let's differentiate t. Quite nice because the t just comes up mz double prime. I have now this one is a product rule. Okay. If I differentiate that, I get e to the 1/2 t squared. If I differentiate e to the 1/2 t squared, I get t squared e to the 1/2 t squared. Okay. So now I evaluate these at 0, mz prime of 0 equal to 0, and that is of course expected value of standard normal. So nothing surprising, and the expected value of z squared is mz double prime of 0. That's 1 plus t squared, which will be 1. So that's 1. And so variance of z is also equal to 1. Remember, expected z squared is the same as the variance of z. It's the central moment. Variance of z is a central moment about the mean, and the mean is 0. So variance equals ez squared minus mean squared. Okay, so those things you probably already knew, but we've derived using moment generating functions. Now I want to talk about shifting and scaling random variables. And let's do continuum. There is an analogous thing for the discrete, but it's quite easy because you just have masses at the points in the discrete. So if you double the points, you just double the inputs to the PMF, and nothing else changes. So for continuous, it's slightly different because oh, you can't see it. Okay. So how do I shift it? If x is continuous with density function f subscript x, then let's do y equals ax plus b. Whenever I use lowercase, I intend it to be constants. So a and b are real constants. And let's say that a is not 0. What would happen if a was equal to 0? A was 0. It becomes a constant random variable. So then y would actually be a deterministic variable, one that's always equal to b. That's not even continuous, so I don't want to try to write down a density or something. So if we're a, b, in R are constants and a is not 0, I just need to figure out what the density is going to be. We know that the probability that y lies between let me do it using the kind of approximations that I was talking about before, because we can say that the probability that x lies between a certain range, x plus dx. This is, of course, I'll even use the asymptotic. Well, I don't want to use dx as an actual symbol, so let me just say x plus d. D can be some short distance. And this will have the behavior of fx of x times the length of the interval as d tends to 0. Okay? But this is, of course, also the same as the probability that y, which is ax plus b, should be between ax and ax plus ab. Now that's in the case a positive. The case a negative is slightly different. Now that should be also asymptotic to f, the density fy of the point that's relevant. The relevant point is y being ax, times the length of the interval. The length of the interval in this case is a times d. So if that's the case, then fy of ax is going to be equal to so these things have to be the same because they're the same. There's only one possible asymptotic behavior. So this is a times fy of a equals fx of x, because those things have to be the same. Effectively, this thing has to be the same as that. So fy, I'll rewrite it in terms of y equals ax. Fy of y equals, and then x is y bracket, fx of x divided by a, and then I have to also divide that by a. So if you stretch the upshot of this, if you stretch out your variable by, say, a factor of 2, then the density actually goes down by a factor of 2. And that should make sense in terms of the density having to integrate to 1. Really, that's all that this is about. If the density of x looks like this, it doesn't have to be null, but I'll draw a null. And then I stretch everything out by a factor of 2. And of course, you have to map corresponding points to corresponding points. So that would be y equals 2x. So the x over a is just matching the y corresponds to ax. So answer. So y divided by x. Because x equals y divided by a. That's the change of variables. But in addition to the change of variables, you have this important dividing by a. And that's to ensure that the total area under the curve is still 1. So fx y of y is, in that context, it's 1/2 fx of y over 2. Y over 2 is the corresponding x value, and you have to multiply it by 1. Okay, if a is less than 0, it's slightly similar, but we don't want to be dividing by a negative number. So it turns out that the direction is just flipped. So fy of y equals yeah, and there's okay. I realise that I've actually done it in the case where there's no shifting. So here I'm just doing scaling. I'm not shifting in this example. Shifting we can do as a separate step, and luckily that one doesn't change the density. So fy of y is equal to fx of y divided by a. That's still the right change of variables, but divided by a, by absolute value of a. And this formula actually works for any. So if it's negative, you have to change to an absolute value, but that absolute value formula works whether a is positive or negative. Where if y equals a. Okay, so that's your changing. And then shifting, I'll just do this separately. Once again, okay, I'm not going to reuse the letter y. If, let's say, u is equal to x plus a constant, b constant, then it should be no surprise that the density of u at a u value is the density of x at the corresponding x value. But, the x value has to be got from the u value by subtracting b. So that's how you shift densities. let's apply this to a standard, non-standard normal. So normal random variable x is said to be normal mu sigma squared. If, well, one way to define it is it's a normal with mean mu and variance sigma squared. Another way is that x is equal to the mean plus the standard deviation times z, where z has a normal 0, 1. Okay, those are equivalent definitions. And this definition is better because it allows us to use the shifting and scaling. So sigma z, so we know that fz of z. So if we just start with the standard normal, we already know this one, 1 over root 2 pi e to the minus z squared divided by 2. If I start with the same thing for sigma z, so I'm just imagining y equals sigma z, we have to use the formula for scaling. So the density of the sigma z random variable at y, I have to evaluate the density itself, 1 over root 2 pi. Now, we assume here that sigma is positive. There's no gain in having it negative because sigma squared will be the same either way. So that's a convention that's always used. And then I take the density, even the minus, I have to substitute z equals y divided by sigma. Y divided by sigma squared divided by 2. And then I have to do it divided by 1 over sigma because that was the scale factor. So that's 1 over square root 2 pi. Now sigma is outside the square root sign, that's important. I guess you could put variance under the square root sign, but the sigma itself is outside the square root sign. E to the minus y squared divided by 2 sigma squared. So that is the density of, that is for y, then still has mean 0 because all I did was stretch. I didn't, I scaled, I didn't shift yet, so that's normal sigma squared. So let's have x now is normal mu sigma squared. The density of fx of x is equal to f density of y. I mean, I don't know why I did sigma z there. I could have also written density f subscript y. I have to evaluate it at the right y value corresponding to x. So if x is going to then be y plus mu, just to give it the right mean. So y value is equal to x minus 2. Okay, so the density of a general normal mu sigma squared is 1 over square root 2 pi sigma outside the square root e to the minus 1/2 x minus mu squared divided by sigma squared. So you could put that all in one fraction. So I guess you could remember this formula if you like, or you could remember just how to scale effectively. This makes sense because z equals x minus mu divided by sigma. That's the way that you transform. So this is nothing other than e to the minus 1/2 z squared, and the only extra factor we got was 1, which is 1 over sigma, and that's just to make the whole density integrate to 1. Okay. So that's normal, and then if you wanted to do that, we can also do the MGF, expected value e to the tx. Right? That's mx of t. You don't have to. I don't want you to always think, oh, I must jump to the density to do that. You could use the same method, but an easier way is just to express it as a transformation of a known random variable. So that's the expected value of e to the t mu plus sigma z, right? Because our general normal random variable is nothing other. By the way, I hope you know that the word Gaussian is synonymous with normal. Many people prefer that because normal is such a complex, named after Carl Friedrich Gauss. If any Gaussian or normal can be expressed in terms of the standard normal by putting mean plus standard deviation times that. So that is e to the t mu as a common factor. It can be brought out the front, expected value of e to the t sigma z. Okay, so that's e to the t mu. Now there's a clever thing here. You can just notice that whenever you have expected e to the something times z, that is itself the moment generating function of z. It is itself mz, but not evaluated at t. It's evaluated at a different point. Can anyone see what I'm talking about here? Let's just recall for ourselves the definition mz of t here. E to the 1 half t squared. That's true no matter what real number you care to substitute in there. Which is, and in case you forgot the definition, expected value of e to the t times standard normal. Now, t there is a placeholder. You're allowed to substitute anything you like as t. So if we go back, what do I substitute? Instead of mz of t would be expected e to the tz. Yeah, so this is mz of t sigma. So you see, it's just a matter of substitution. You can save yourself effort by doing, you don't have to restrict the MGF to when the letter is t. You can do it for any substitution you like. And that means that this is e to the t mu. We've already done the formula, e to the half of parameter squared. So in this case, it's t squared sigma squared. Okay? So you could put all those in the same exponent if you like. E to the t mu plus 1 half t squared sigma squared. So we've already got the moment generating function of the norm. So I want to go on a little bit. I'm not going to talk about the general way. Shifting and scaling are actually part of a general way of transforming random variables. For the moment, I'm not going to talk about general transformations. I'm just going to do some fairly directly. And one of the best ways to do that is the CDF, because the CDF helps you understand quite a lot. So let's try to understand now the square of a normal random variable. X is just going to be defined to be z squared. Right? So this is a different x from the previous page, where z has a normal 0, 1 distribution. Now I could go ahead and try to find its mean and variance directly with that formula of, remember if you have a function of z, expected g of z is integral g of z density of z. So we know how to do that. But let's try to understand it with the actual density and distribution functions. And the best way to do that, well, there are many ways, but if this is a squared, so x is now always a non-negative random variable, but it should still be continuous because z takes the continuous random values, so should x. Let us talk about, rather than the density, which we haven't yet proved in this class how to transform a density under something that's. This is not just a shifting or a scaling because it stretches out more when z is large, it stretches out less when z is small. The derivative is not constant. So rather than try to understand that in general, let's just try and do it specifically. The probability that x is less than or equal to x. So this will of course be f subscript x of little x. Probability x less than or equal to x is the integral. Well, okay, before I do that, it's the same thing as saying that z squared has to be less than or equal to x. So I would only really be interested in this for x positive. For x negative, I know there's 0 chance of being, because I know that x is non-negative. So I'm only interested in this for positive x. Oh, you could include 0 if you like. And just as a matter of fact about, these are all real numbers, if z squared is less than or equal to x, we know that z is less than or equal to the square root of x. That has to be the case. Is there anything else we know about z? I sort of want an equivalent statement. When you have equalities rather than inequalities, you've got to be particularly careful about, derivations one way versus having an equivalence, which should be, this is not yet equivalent because, for instance, minus 1,000,000 squared is much bigger than x. So I want some other constraint on z that it's not too small either. Minus square root x. Now this is a equivalent statement. You can remember back to quadratic functions and so on. It only has a unique minimum in the middle, and then it's increasing on either side. So that's So now this is, I just want to emphasize, to say that the probability of two events are the same, you have to say that those events are equivalent, not just one implies the other. Otherwise there would be a greater than or a less than sign between the probabilities, not an equal sign. For it to be equal, I have to have a true equivalence. And now I can write that as, well, I could write it in terms of the, there's two ways to do this, in terms of the actually writing down an integral, or we could just write this as phi of square root x. Now that itself would give you the chance of being less than or equal to square root x, but I have to subtract all the ones that are less than minus root x. Minus square root. Does everyone see what I did there? Because you could write, if you want to go by integral, you could do integral from minus root x to root x, and then you do that as a difference between two integrals, one from minus infinity to root x, and one from minus infinity to minus root x. Because of course, this is, another way to do it is it's just two events. The event of being less than or equal to root x, and then subtract the event of being less than or equal to minus root x. So it's a set difference, that's another way to say it. So this is good, because then the density of this, so long as this is differentiable pretty much everywhere, you can use the following derivation. It is the derivative of this, of capital A. So it is, of course, f x over x, and then so that equals d by dx of this thing, phi of root x. Now remember, phi doesn't have a closed form, but the derivative of phi does. For the moment, I won't substitute that exactly, but so now am I right in doing the following thing? Phi prime of root x minus, okay, well, this is kind of a straw man. What have I done wrong here? Yeah, I haven't used the chain rule, and I should have, because you can only differentiate the function just by getting phi prime itself if you just had x inside, or x plus 1. Here it's phi of a function u of x, u equals square root x. I have to multiply by du by dx, which is 1 over 2 root x. 1 over 2 square root of x. So that's now correct by the chain rule. Now for this one, it's the same, except I'm not doing derivative of root x, I'm doing derivative of minus root x. So that would be minus 1 over 2 root x. I'll put the 2 root x here, and the minus times minus will become plus. So this is equal to, now capital phi prime is of course lowercase phi. And lowercase phi is symmetrical. So under phi of square root x divided by 2 root x. But of course, this is times 2, because little phi is the same at root x versus minus root. It's an even function. So I get a 1 over root x times, now just the phi, 1 over root 2 pi, e to the minus 1/2 input squared, remember it's half z squared. So I can't put x squared, I have to put square root x squared. Okay? So simplifying, that's e to the minus 1/2 x, and I'll put 1 over square root 2 pi x. Okay, and that's for all x positive. Now, I'm just going to, we're almost at the end here. We've deduced the density of x equals z squared. Definition, this is actually called, x has the distribution called chi-squared 1. And the meaning of that is the sum of squares of one standard normal. So just the one squared standard normal. The word used is chi-squared. Okay? With one degree of freedom, that's effectively one dimension of normality that went into it. I just want to compare one other distribution that I'll introduce, x, which is gamma, with parameters a and b, if the density of, so this is slightly different because it can allow any parameters a and b, is equal to x to the minus x to the a minus 1, e to the minus b x divided by b to the power a, gamma of A. Now, what is gamma of A? Once again, it's the only function, and this density is only for positive x. A gamma density is only for positive x. You can actually find that chi squared 1, you can double check this, equals gamma. These are